Thanks for the introduction. The title of my talk is Differentiable Causal Discovery from Interventional Data. My name is Sébastien Lachapelle, and this is joint work with people from Mila and LMNTI. Okay, so let's start with some motivation. So here's an example of a medical study. So we have patients which suffers from kidney stone, and you want to, so they suffer from kidney stone, and they receive different treatment, and you look at whether they recover or not. And so you have three variables. You have T, the treatment, S, the size of your stone, and R, whether the patient recovered or not. And on this side, you have a causal graph, which tells you how these variables are related to each other causally. So basically, it tells you that the recovery is caused by both the size of your stone and the treatment you received. And it also tells you that the treatment is caused by the size of the stone. And this is the case because you can imagine that the doctor will decide your treatment based on the size of your stone. And so that's why you have this causal arrow here. And so you can collect data about in a hospital or something, and you get these results. So the table gives the recovery rates for different subpopulations. And so the first column tells you the recovery rates for people who took treatment A and for people who received treatment B. And if you look only at this column, you might be tempted to say that the treatment B is better than treatment A because the recovery rate is higher. But if you look more closely at the data, and instead of conditioning only on the treatment, you condition also on the size of the stone, the picture is a bit different. So you have that no matter what's the size of your stone, the treatment A seems to be better. And so if you want to pick the best treatment for you, so if you want to maximize your chance of recovery, which treatment should you take? And to try to understand this, I will ask you two questions, which I think are very similar, but are actually different. So the first question is, what is my chance of recovery knowing that the doctor gave me treatment A? Second question, what is my chance of recovery if I decide to take treatment A? And in both cases, you can assume that I don't know the size of my stone. So I'll try to convince you that these two questions are different. And so to answer the first question, you can just look at the table that I showed you. And basically, you look like among people who receive treatment A, what's the proportion of people who recovered? And this is probably a good estimation of what's your chance of recovery knowing that you received treatment A. But in the second question, the setup is a bit different. In some sense, the causal graph associated to this question is a bit different. So when I'm asking what's my chance of recovery when I decide to take treatment A, in some sense, my decision of taking treatment A does not tell me anything about the size of my stone. So I'm not deciding my treatment by looking at the size of the stone like the doctor did before. Okay, so it seems that like the setup is a bit different for both questions. And if you want to answer this question quantitatively, you need to do some more work. You cannot just look at the table that I showed you, and it requires some more computations. It's actually very easy computation, but we won't do it. And so yeah, and I would argue that the second type of question is maybe more interesting because it's really about making decisions. So if I want to maximize my chance of recovery, which treatment should I pick? So, and this is basically causal inference is really about trying to answer the second type of question. And you will do that by using data, but also a causal graph. And actually, the answer to this question will really depend on the causal graph that's underlying your situation or your data. But the problem is that in many applications, this causal graph is unknown. Okay? And so the solution is to try to learn it. Okay? And so causal discovery is the problem of learning your causal graph. And so you get various kinds of data, and your algorithm will try to output a causal graph. And you can, you could be using different types of data. In our case, we use observational data and interventional data. So observational data is just the data we are used to in machine learning. So it corresponds to the table that I showed you before. Interventional data is data that comes from controlled experiments. And I'll try to illustrate what this is with, again, this example. So in this slide, I'm trying to illustrate two kinds of interventions. So perfect interventions and imperfect intervention. And so a perfect intervention on the treatment variable could be that you remove the doctor from the hospital and you replace its decision by a coin flip. So that would be a randomized control trial. And by doing that, you remove the connection between the stone size and the treatment. And so an example of an imperfect intervention would be, again, removing the doctor, but replacing it or replacing him by another one. And so this new doctor will still base his decision on the size of the stone, hopefully, but he will maybe make his decision differently. So maybe we'll have different preferences in terms of which treatment you should have. And so if you're familiar with probability distributions, here you have like the factorization of the distribution according to the graph. And an intervention corresponds to, so an intervention on the variable t corresponds to changing a conditional in the factorization. So so to go from there to there, you just change the conditional of the treatment variable. Okay, so you can think of this as just changing one mechanism in your distribution, or one mechanism in your in the way your data is generated. And so I think it's important to realize that imperfect intervention are actually more frequent. So you can imagine having data coming from different hospitals, and in some sense, in each hospital you have different doctors, and so maybe you can sort of interpret these different data sets as different imperfect interventions. And so you could potentially use this data to learn a causal graph. Okay, so I now arrive at our project. And so our project is to propose a causal discovery algorithm called DCDI. And so basically this algorithm can leverage various types of interventions. It relies on continuous constraint optimization and neural networks. It does not make strong assumptions about the causal mechanisms thanks to expressive normalizing flows. It is also theoretically grounded, and it compares favorably to state-of-the-art methods. Okay, so the setting is the following. So you assume you have access to D variables, and you assume that they are causally sufficient, which means that you don't, there's no hidden variables. You observe everything. And we encode the causal graph with a matrix G. So it's an adjacency matrix. And so it tells you how the different nodes are connected. And you also assume that you have access to interventions that could be potentially imperfect. And so, so you have to imagine you have access to like many different data sets. And for each data set, one of the variable is targeted by an intervention. And so all this information is encoded in this intervention matrix. And so for instance, this matrix is telling you that in the first data set, no variable is targeted, so there's no intervention. And it tells you that in the second data set, variable 2 and variable 3 are targeted. Okay, so how does DCDI learn a causal graph? And so it learns a causal graph by fitting a model, basically. And the model goes like this. So for each variable, you have a neural network that takes as input its parents according to the graph G. And this is done by masking the input of the neural network. Oops. And each neural network will output a conditional distribution. And if you take the product of all these conditionals, you get a joint density. So is this the, okay, 5 minutes left. And so what's important here is, yeah, so, and you will use the information about the interventions to decide which variable will be allowed to change their parameter. Okay, so basically for variables which are targeted, so that's when ikj is equal to 1, you will use a new parameter that we use that we call interventional parameter. And when there's no intervention, you will use the observational parameter. And basically, this model is trying to mimic the definition of intervention that I showed you before. And so, since we want to learn the causal graph using continuous optimization, we will do a relaxation or a stochastic relaxation, which basically amounts to treating this discrete matrix as a random matrix with continuous parameters. And so instead of optimizing over the space of graphs, you will be optimizing over the continuous space of parameters. And so the optimization objective looks something like this. So basically you want to fit your model for all the on all the interventional distribution. So on all the interventions. And also you want to make sure that your graph is acyclic. So yeah, I'm not explaining why this means acyclicity, but it's actually the case. And to solve this problem, we use a mix of classic continuous constraint optimization and maybe more modern deep learning techniques. Okay, and so up to now, I have assumed that the targets, so I've assumed that for each data set, we knew which variable was targeted, but it might not be the case. And it turns out that you can sort of adapt what I just showed you to make everything work in the case where you don't know the nodes which are targeted. And you do that by doing the same kind of relaxation that I showed you before, but now you do it for the matrix, for the intervention matrix. But yeah, and so we also have theory for both cases, for known and unknown targets, and everything works fine. And in practice, we also have interesting results. And so, yeah, I think I'm already out of time. So in a nutshell, we have good results, and it seems to be working better than the other methods, especially for denser graphs. So thank you.